Intelligence can be measured as the application of knowledge. So hence your intelligence of or in a particular field of study is not measured by how well you remember and recite ideas or concepts in that field. It is measured by how well you can apply those ideas and concepts. So you have people on your platform, Brother SANETER, and I'm not going to call them names, but they brag about, I can remember this, I can recite this. And so I'm sure you bring taxonomy, family. And you see at the bottom, right? The bottom of the hierarchy of thinking is remembering. Okay? And so, Brother SANETER, I'm not going to call them names.
Can't hear you. Unmute yourself. I just unmuted you.
Yep, that's exactly what it was. I was like, peace and love, Brother SANETER, and going in. But peace and love to you, Brother SANETER. Thank you for allowing me to come on this platform to have this discussion. I know that there's a lot of discussion about 5G and electromagnetic radiation and signals and frequency. And, and that's all kind of intertwined with this coronavirus pandemic going on. People are actually trying to make these connections, right? And so there are a lot of discussions going on. And this is good. I mean, it's actually a really good thing. I'm glad that these discussions are happening. I'm glad, Brother SANETER, that you're showing both sides of the argument. So some people, they're for, the technology. Some people are against it. And so you're showing both sides of the argument. So I'm happy that we're having this conversation. I want to say peace to you and peace to Brother Kyle. There's the brother that I'm on the platform right now. His name is Brother Kyle. Brother Kyle has a bachelor's, I believe, in network engineering. He just did a wonderful presentation on the Real Black Atheists on Fire YouTube channel. So when you all get an opportunity, please go and check that out. Brother Kyle, do you want to introduce yourself or say something before I get started?
Yeah, peace to the family. Black Power first and foremost. I'm Kyle. I am a network engineer. I've been in the field here pretty recently. So I'm a recent grad from DeVry University. And I'm just excited to hear your presentation and salute to you, Queen.
And thank you so much, brother. So I also want to say peace to the brothers and sisters in the chat room. Thank you for tuning in. But Brother SANETER, thank you for showing Meltrek. You know that's my flagship project that I've been working on for a few years now. And so that was Meltrek episode 3. Be on the lookout for that, family, in August of this year. We should be dropping Meltrek episode 3. The video, Brother SANETER, that you showed me was one of my students at Morgan, and he was demonstrating a project. So I teach a class called Electric Circuits, and typically towards the end of the semester, I assign them what's called a design project. And so he was showing you his design project in a lab, right? And so a lot of people who are talking about signals and voltage and frequency and this and that and this and that, they've never been in a lab. And so I'll get to that in a few SANETER. So I'm gonna go ahead and share my screen. Sai, let me know if you see it. Let me know if you see it, Sai.
I see it. It's up.
Okay. So 5G, RF signals, wireless communications, radiation. What does it all mean? All right. So I want to give the family some food for thought. Intelligence can be measured as the application of knowledge. So hence your intelligence of or in a particular field of study is not measured by how well you remember and recite ideas or concepts in that field. It is measured by how well you can apply those ideas and concepts. So you have people on your platform, Brother SANETER, and I'm not going to call any names, but they brag about, I can remember this, I can recite this. And so I'm showing you Bloom taxonomy, family. And you see at the bottom, right? The bottom of the hierarchy of thinking is remembering, okay? And so you're really at the lowest level. Let me go back. You're at the lowest level of thinking when you strive to just remember things. So remember means to recall facts and basic concepts, define, duplicate, list, memorize, repeat, and state. And so this is the lowest level of thinking. And what I do in my engineering courses is I encourage my engineering students to climb up the hierarchy of thinking. So I bring them to a level of understanding ideas and concepts, being able to explain them, identify them, recognize them, and then apply those ideas and concepts to, like I said before, design projects. So they actually use the information in new situations. And then not only use the information side of it, but also analyze. So being able to apply these ideas and concepts and then analyze and also evaluate what we do. And once you reach the apex of thinking, you will have produced a new or original work. So that means that you will have added to the body of knowledge that already exists. Okay, and typically when people get a PhD, that's what that signifies. It signifies that you have reached the hierarchy of thinking. You have created something new. You've added to a body of work. Okay, and so that's what that signifies. So the objective of this presentation is this. Although people have always been concerned about the effects of modern technology on the human body, the rolling out of 5G has heightened the concerns. Intelligence in the fields of biology, physics, mathematics, and electrical engineering is required to understand and address these concerns. So the goal of this presentation is to provide viewers with a basic understanding of 5G, signals, wireless technology, and radiation in order for them to, one, engage in fruitful discussion, and two, be able to formulate good questions and educated opinions regarding the effects of 5G on the human body. All right, so these are my references, family. These are books that I've actually read as a student and actually it also used to teach courses at Morgan. The first book you're looking at is called Signal Systems and Transformations. It's the 5th edition by Phillips, Carr, and Riskin. This is a book that sophomore level students are using at Morgan and at a lot of universities in the ECE departments, okay? And Signal Systems and Transforms is actually one of the required courses for an ECE major. When I say ECE, I'm saying electrical and computer engineering, okay? The second book is a book entitled Wireless Communications by Rappaport. This book was heavily used in the earlier years. I believe it was published like in the early 2000s, but people still use this book because it provides a very strong foundation on wireless communications, so we still use it. And also, and lastly, Digital Communications, Fundamentals and Applications by Sklar, okay, Bernard Sklar. And so we also use this. And as I said, both of these books are rather dated, in my opinion. They were published almost maybe 20 years ago or 18 years ago, but they give a solid foundation on wireless communications and digital communications. And so we still use these as a resource. Now, if the information did not come out of these textbooks, then you'll see on the bottom of the slide my reference, okay? So let's move on. Let's first look at the roadmap of evaluation towards 5G communication. So I want to take you back to 1983 or before 1983. So that was before 1G existed. So before the advent of 1G, all wireless communications were voice-centric. Okay, and it used analog systems with it says single sideband modulation. So essentially, we weren't sending data, everything was voice centric, and they used analog systems. And I'm going to get into what analog systems are a little later in this presentation, okay? And I'm also going to get into what modulation is. But I wanted to stick with you that prior to 5G, wireless communications, they were voice centric. They used analog systems, and the modulation scheme was what they call single sideband modulation. We'll get into that a little later. Okay, so when 1G came around in 1993, they were still using the wireless communications were still voice centric, and they were still using analog systems because digital radio systems were very expensive. When 2G came around in the 1990s. This is when they changed, or they went from using analog systems to digital systems, okay? And then they also started implementing different, they call it channel access schemes like TDMA, and I hope you can see my cursor right here. So TDMA stands for time division multiple access, multiplexing, okay? And so all of this is just a way to access the channel. So they were using TDMA multiplexing, okay, with 2G, and they were also using digital systems, okay? So when 2.5G came around in 1995, they then started using another channel access technique called code division multiple access, which used a 1.25 megahertz bandwidth, all right? And when 3G came around in 1999, they started using something called YCDMA, wideband code division, multiple access, but the bandwidth you see right here was 5 millihertz. So you see, as time went on, they started developing more channel access techniques, and the bandwidth increased, right, with each generation. So in 2.5G, they used the 1.25 megahertz bandwidth, but with 3G, they used a 5 megahertz bandwidth, okay? And it said it operates in both frequency division duplex and also time division duplex modes. And so we will get into that a little later on in the discussion. 4G came out or rolled out around 2013, okay? Now this was high-speed data rate. Oh, let me go back, guys. Let me go back. In 3G, I neglected to say that you had voice and data capability, okay? But 2G, you had voice with limited data service. 3G, you had voice and data capability. And then we made it to 4G, where you had high-speed data rates plus voice system. And so this whole paragraph just talks about like the bandwidth for the different systems was at least 20 megahertz. They use different channel access techniques. You had OFDM, which is orthogonal frequency division multiplex. And again, these are just channel access techniques, okay? But what's important is to know that with 4G, you had high speed data rates plus a voice system, and the bandwidth also increased. So remember, in 3G, the bandwidth was at 5 megahertz, but 4G, you see that we're up to about 20 megahertz. Okay, so now we have 5G coming out. It should be rolling out in the 2020s. I believe they said by 2025. But you have 5G, coming out, and with 5G, we'll be able to send data faster than in the previous generations. So let's take a look at this table. So you see with 1G, 2G, and 3G, well, they have a data rate for 3G. You were able to send 384 kilobits per second, right? 4G, 100 megabits per second. But with 5G, they're estimating that you'll be able to send or transmit 1 gigabyte per second, okay? And so you see the comparison here. So we'll be able to send more data because the bandwidth is going to be much greater than 20 megahertz. So we'll be able to send more data at a faster rate, okay? So 5G is the 5th generation of wireless technology. All right, so what are the benefits of 5G? You have faster data rates. It's going to reduce the latency virtually to zero. And what they mean by latency, they're saying the delay. It's going to reduce virtually to zero. So there won't be any delay in trying to connect and get responses and things of that nature. You'll be able to handle many more connected devices. The 5G towers are small and they'll require less power. Now, the concerns of this, with 5G, we will be operating at higher frequencies, okay? And 5G towers are smaller, and so you're going to need more towers to cover the same space as the 4G towers, okay? So the towers are small, which means you're going to need more towers, and more towers mean more exposure to radiation, all right? But 5G is really, I'm telling you guys, it's literally going to change our lives. It's going to enhance the existing devices that we use and also create new devices, okay? And so our smart homes, our buildings, and our cities, I'm telling you guys, this one you're going to feel like you're literally in the space age when 5G hits, okay? And so it's going to affect our homes, our buildings, our cities, our vehicles, the wearables, our watches, our sensors, okay? Even, indoor and outdoor stuff, venues, stadiums, okay? So it's gonna be like living in a totally different world when 5G hits. Okay, so I noticed that a lot of brothers on the platform are having conversations about 5G. So they're mentioning signals, frequency, radiation, wireless technology, but they really don't understand the basics. And neither does the viewers, to be honest with you, SANETER. And so I wanted to have a conversation about the basics of this stuff so that when we're engaged in dialogue about 5G, we can have a fruitful dialogue. People can ask educated questions and formulate educated opinions, okay? Or good questions and formulate educated opinions about the subject matter. But in order to do that, we have to understand the basics. So I want to start off with what's a signal. I mean, we hear that a lot. What's a signal? What's a signal? Back when I took signals and systems, and I took that class probably 20 years ago when I was an undergrad at Morgan, my professor, her name was Dr. Pamela Lee Mack. And I took her class, and she defined a signal as a phenomenon that has a characteristic of amplitude and varies with time, okay? And so that was her definition. And then as I went through, matriculated through graduate school, and I started studying signals heavily, I came across other definitions. So this is a definition that I came across by Dr. Purnachandra. And he said that a signal is defined as a function of one or more variables which conveys information. He also said that it's a physical quantity that varies with time in general or other independent variables. So I felt like he provided a little bit, I don't want to say a better definition, but I felt like it was definitely a more detailed definition. Okay, and then Princeton University, they published a paper, and in the paper they said that a signal is a physical or abstract quantity. So it can be physical, it can be abstract, right? But it can be measured, or it influences one that can be measured, okay? So that's a signal. So essentially a signal is a phenomenon. It can be physical or abstract, right? It conveys information. It's a function of one or more variables. It varies with time. It has the characteristic of an amplitude. And most important of all, it can be measured. A signal can be measured. So examples of signals would be a radio signal. You have a broadcast or cable television signal, or you can have a voltage signal, right? A voltage signal, okay? There are different categories of signals, okay? So you hear people will talk about continuous time signals or discrete time signals in literature. You'll also hear people refer to signals as periodic or aperiodic. And what they mean by aperiodic, they're just saying that it doesn't repeat, it's aperiodic. They also talk about even and odd continuous time signals. An even signal is a signal that is symmetric about the vertical axis. An odd signal is a signal that's symmetric about the origin. So sometimes in literature, you'll hear people talk about even and odd signals. Then you'll hear people also talk about deterministic signals and random signals. So a deterministic signal will be a signal that you already have the values and you already know the values for. So for example, the cosine function, that would be a deterministic signal, okay? The sine function would be the sine function would be a deterministic signal because we can literally plot cosine and sine, right? An exponential would be a deterministic signal because we can plot an exponential, we know what that looks like. A random signal would be a signal like noise. We typically don't know what noise is. And so when we're running experiments, we assume, they say AWGN, additive white Gaussian noise. So we assume that the noise has a Gaussian distribution. But noise would be like a random signal because you just don't know what the value is going to be. And then we have energy signals and power signals, okay? And the difference between an energy signal and a power signal happens very instantaneously, okay? Very instantaneously. And so with a power signal, if you were to plot that or look at the power signal on a frequency spectrum analyzer, you'll typically see an impulse function there, which shows you that it happened instantaneous, basically. All right. And so what is a continuous signal? A continuous signal is one that is defined over a continuous period of time. So there aren't any breaks, okay, in between time. A common signal is the analog signal. So remember when I showed you, when I was going through the evolution of 1G, 2G, 3G, and 1G, and before 1G, I mentioned that they used analog systems. Well, analog systems dealt with or processed continuous signals, okay? And it's continuous signals, so we refer to those as analog signals, okay? So an analog signal or continuous signal has values for all points in time in some possibly infinite interval, okay? And the amplitude of the signal varies continuously with time. So let me give you what that looks like, okay? A diagram of what that looks like. And so this is a continuous time signal, okay? You see on the vertical axis, we have T, we have time. On the, this is the horizontal axis. we have t, which is time. On the vertical axis, we have amplitude, okay? And so this is what a continuous time signal looks like. It's continuous, you don't see any breaks, all right? And so an example of a continuous signal would be a speech signal, a ECG signal from your heart. Of course, your heart needs to be continuously pumping, right? Because if it's not, you'll be hit. Okay, temperature variation over a time interval, or atmospheric pressure variation over a duration of time, okay? So then you have a type of signal called discrete, right? And a discrete signal is one where the independent variable takes on a discrete or finite set of values. So let's look at that, okay? So again, on the vertical axis, you have amplitude, on the horizontal, you have time, but notice that it's not continuous, right? You have amplitudes, that you have a signal that has an amplitude at specific instance of time. So at negative t, 0, t, 2t, 3t, 4t, 5t, 6t, okay, and it continues. But this is what a discrete looks like, a discrete signal looks like, okay? So it has values only for discrete points in time, okay? And again, the amplitude of the signal varies at every discrete end, okay? Now let me show you this right here. You can obtain a discrete signal by sampling a continuous time signal. So that's what I'm showing you in this particular diagram. So suppose you have an x of t, that's a continuous time signal, and you wanted to sample this to produce a discrete signal. Then you would just multiply this by a summation of pulses, and that's what this is. It's a pulse train, okay? And if you multiply the pulse train in the continuous time signal, this would give you points, okay? You would get something that has points. All right, let me go back. Okay, and so basically you can create a discrete time signal from sampling a continuous time system. Continuous time signal. All right, signals are periodic. I know that we're talking about frequency, but we got to remember, in order for something to be operating at a certain frequency, it has to be periodic. And so we have to understand the idea of periodicity, or the concept of periodicity. Okay, and so suppose you have a signal, and let's call this signal x of t. Okay, a continuous time signal x of t is periodic if and only if there exists a t naught greater than 0, such that x of t plus t, or t naught, is also equal to x of t for all t. So what you're saying right here, what this equation is saying, is that at that point t, the signal repeats and it looks like the original signal. So it's kind of like you're looking at duplicates of the signal as you go along the vertical axis. So at t naught, your signal is actually repeating, okay? And so we call that the fundamental period of the signal, all right? Now, if the signal does not repeat, we refer to that as an aperiodic signal, all right? So right now you're looking at a periodic signal. And so my question to the audience would be, well, what is T naught, okay? And so T naught would be the point at which the signal repeats. And so we see that the signal goes up, it comes down here, it goes up, and then it makes its way up again. And so the point at which it repeats is 2 pi. So for this particular graph, T naught, or the fundamental period, meaning the first time that it repeats, would be at T naught. And T naught in this case is equal to 2 pi. Okay, now, so T pi is essentially the time it takes to complete one period. We call that one cycle. And frequency is the number of cycles per second. Now, the standard unit of frequency is hertz. So I know we hear that 1 gigahertz, 2 gigahertz, 3 gigahertz, 20 megahertz, right? But when you talk about hertz, you're talking about cycles per second. Okay, so how many times does this signal repeat per second, right? And so the frequency is the frequency is equal to the reciprocal of the period, okay? So F naught, the frequency, we call that the fundamental frequency, is equal to 1 over T naught. And so T naught would then be equal to 1 over F naught, okay? And so frequency can be expressed in radians or hertz, okay? Right here is expressed in hertz, but if we want to express it in radians with omega naught is equal to 2 pi over F naught, where F naught is in hertz, okay? And so that will result in radians per second. We can also express omega naught as a function of T naught, which is the fundamental period. And so here, omega naught is equal to 2 pi over T naught. Okay, and I already said that T naught can be expressed in terms of frequency in hertz and radians. Up here, I said that T naught would be equal to 1 over F naught, and we see that down the bottom. But we can also express T naught as a function of radians. So in that case, T naught would be equal to 2 pi over omega. And you can see, you could have deduced that right here when you just did a variable switch. You would put T naught here and omega naught there. You get the same thing, okay? So signals can be viewed in the time domain and in the frequency domain, all right? In the time domain, you're dealing with seconds, minutes, hours. Frequency domain, you're dealing with hertz and radians, okay? And so we can go, or we can look at a signal in the time domain and then analyze that same signal in the frequency domain. But we would have to convert that time domain signal, okay? And so there are techniques that we use. One technique is called the Fourier series, the other is called the Fourier transform. Okay, so we use these techniques to convert a time domain signal to a frequency domain signal, all right? All periodic signals, both continuous time and discrete time, have what we call a Fourier series representation. So when you plot the Fourier series, you are essentially looking at that time domain signal in the frequency domain. Okay, so if the signal is periodic, it definitely has a Fourier series representation. It also says down here that all periodic signals, both continuous time and discrete time, have Fourier transform representation, okay? And so when you plot the Fourier transform of an aperiodic signal, and even of a periodic signal, you're looking at it in the frequency domain. All right, so let's get into how this is done. So a signal that is periodic for some positive value t, so x of t is definitely periodic, okay? Where t is the fundamental period, and down here you're looking at a graph of x of t. So this is a plot of x of t right here. So how do we look at this signal in the frequency domain? Well, what we do is we approximate, or we use what's called a sinusoidal approximation of x of t, okay? Because remember, sinusoids repeat, okay? And so we would use what's called a sinusoidal approximation of x of t in order to look at it in the frequency domain, okay? So hence, the Fourier series says this, that a periodic signal can be decomposed to a summation of sinusoids or complex exponentials that are harmonically related, okay? And so this is what you're looking at right here with this equation x of t. X of t is equal to sigma, or the summation of a, so a is the amplitude of the sinusoid, times k omega t, so you're looking at the frequency, or the omega, the frequency, plus the phase, which is phi. Okay, so essentially x of t is now a summation of sinusoids, and that's what we did back here. We had a continuous signal that was periodic, and we used a sinusoidal approximation in order to view it in the frequency domain. So let me go back to this, okay? So essentially, x of t, if we rewrite this, so you're looking at x of t expressed as a summation of sinusoids, but remember in the definition I said that it can also be decomposed to a summation of complex exponentials. And so that's what you have right here. X of t is equal to a summation of e to the jk omega t, omega naught t. This is a complex exponential.
Hey, Dr. Maat.
Yes?
I'm sorry, but I got to say this real quick, and I'm going to let you go back in so the viewers won't be disturbed. Some of the people are saying, all those people that's in here that's saying this is boring, the only reason why it's boring to you is because you're not used to learning. You're not used to studying. You're not used to going to class and learning. So what it is the reason why it's boring is because you're used to people fighting and arguing and going back and forth and all of that. So you're not used to getting knowledge and doing real studies. Like when you go to college and sit down, see, a lot of y'all probably never did that. So a lot of y'all are probably dumb and stupid. So of course it would be boring to you. We are trying to reach the higher up. Those who study, those who read, those who sit back like in the classroom setting. So of course it's going to be boring to you. because you're the stupid ones. But go ahead, Dr. Maat. I had to say that.
Okay, I got you, Sanetta. I'm not even looking at the chat room. I'm just laying it out, you know, and this information that I'm giving the people, typically someone would learn this over the course of a semester. Like it takes a semester to learn about signal systems and transformations. A semester, you spend a semester on wireless communications, a semester on digital communications, a semester on just understanding this math. Like, for engineering, we literally have to take calculus 1, calculus 2, calculus 3, linear algebra, differential equation, and problem stats. Okay, and so these are the courses that you would take over the course of maybe 4 or 5 years at an institution. So what I'm trying to do is just give the people like a basic level understanding. And so my intention, Sanetta, is not to speak over people's heads. I'm trying to break it down as simple as I can. But I'm going to go ahead and continue. Okay, so a periodic signal can be decomposed into a summation of sinusoids or complex exponentials. So here in the second equation, you have a summation of a weighted, complex exponential. So e to the jk omega naught t is a complex exponential. And if you just do a quick Google search on Euler's formula, you'll find that e to the j theta t is just equal to e cosine theta plus j sine theta. And so it has a real, what we call in math, a real and imaginary part. All right. So anyway, the CK is what we would call the Fourier coefficients. Okay. And so the Fourier coefficients, if you were to plot the CK or the Fourier coefficients, you would be essentially looking at the signal in the frequency domain. All right. So this is another equation you can use. This is actually calculus that you're looking at. You can use this equation to solve for the Fourier series coefficients, which is simply CK is equal to 1 over T, and you're integrating over a full period. You're multiplying x of t by a complex exponential. Okay, and that's how you would get the Fourier series coefficients. Okay, and again, once you plot these Fourier series coefficients, you would be looking at the signal in the frequency domain. All right, and so this will require you to at least take calculus 1 so that you can understand how integrals work. So the Fourier transform, Fourier series is a technique, and I already said that, is a technique used to represent periodic time domain signals in terms of their harmonic frequencies. And I'm not going to get into what harmonic frequency components are. Again, that's some math. But let's suppose that you have a signal that doesn't repeat. And so what you do is assume that signal is just one long period. So you would assume that T naught is approaching infinity, right? And so if you assume that T naught is approaching infinity, then it's easy to derive what we call the Fourier transform, okay? And so x of j omega is equal to, now this is the Fourier transform of x of t. And again, you would need to understand a little bit of calculus in order to do that. And so x of j omega would be the Fourier transform of x of t, and you would have to integrate this, okay? And if you want to get back x of t, which means if you want to leave the frequency domain and go back to the time domain, you would have to integrate the Fourier transform, okay? And so this is the equation. I hope you guys can see my mouse. This is the equation right here that you would implement or apply to do so. All right, so let's get into a little bit of communication systems. So now at this point, we understand what a signal is. We understand the different types of signals. We also understand how to compute a period. We understand the relationship between a period and frequency. And we know how to convert signals from the time domain to the frequency domain and from the frequency domain back to the time domain. Okay, so those are pretty much the basics of signals. So now let's get into the basics of communication systems. So what is a communication system? Okay, we know that communications is the process of establishing a connection or link between 2 points of information exchange. Well, then a communication system will consist of devices that employ one of 2 communications methods. It may be wireless or wired, different types of equipment, and various accessories, right? And or enhancements, okay, to transmit and receive information. So this is the block diagram of a basic communication system. Typically you have an input system, and that input system is sent to a transmitter, or it goes through a transmitter. That transmitter, it goes through some processes within the transmitter, and then it transmits a signal. We call that the transmitted signal. That signal then goes through a channel, okay? It goes through a channel, and that channel may be noisy, it may be distorted, it may have some interference. You never know what the channel is. And then it gets on to the receiver end, okay? And it goes through a period where you're trying to deduce or discern or estimate the output signal, okay? So this is how a transmitter looks from beginning to end, and these are the basic blocks of a communication system. All right, so you can have analog communications or analog communication systems and digital communication systems. So remember at the beginning of my presentation, prior to 2G, these systems were analog, right? And when 2G came about, the systems were digital. So in an analog communication system, the message signal to be transmitted is analog, okay? And in a digital communication system, the message system to be transmitted is digital. Okay, and so these are the differences between an analog system and a digital system. I defined for you, what an analog signal is versus a digital signal. Analog signals are continuous, digital signals are more discrete. And so now we know the difference between a continuous signal and a discrete signal. Typically, the waves in an analog system are denoted by sine waves. In a digital system, square waves. It says representation uses continuous range of values to represent the information. With digital system, you use discrete or discontinuous values to represent the information. An example of analog systems, you have human voice and air, analog electronic systems. Digital, you have computers, CDs, DVDs, and other digital electronic devices, okay? And so I wanna make a note here. It says response to noise. With the analog system, it says more likely to get effective reducing accuracy. With digital systems, it says less effective since noise response are analog in nature. And so that's a big difference between analog and digital systems. And so I'm not gonna read all of this through, but I do wanna note that the bandwidth for analog systems, what we have right here, before I get to bandwidth, I want to say that flexibility, it says analog hardware is not flexible. Digital hardware is flexible in implementation. Okay, and then I want to pay attention to the bandwidth. So it says the bandwidth, it says analog signal processing can be done in real time and consumes less bandwidth. So I guess that's a pro for an analog system. With a digital system, there's no guarantee that digital signal processing can be done in real time and consumes more bandwidth to carry out the same information. So that's probably one of the pros and cons of using an analog system versus a digital system. All right. So this is the block diagram, and this shouldn't say digital. This should actually say block diagram of a typical analog system. This is actually a typo right here, family. So it should say block diagram of a typical analog system. So typically with an analog system, you have an information source, and that could be sound, light, pictures of words, and it goes through an input transducer. And what a transducer does is it converts one thing or one form of energy into another, right? And so it converts it. So you have an input transducer that produces an electrical signal. That electrical signal goes to a transmitter. That transmitter produces a signal, or that transmitter produces a signal that is transmitted through a channel, okay? Once it gets on this end, the receiver receives the electrical signal, okay? That signal goes to an output transducer, okay, to now convert it back into a sound, light, pictures, or words, and then it gets sent to its destination. Notice again in the channel, we have some noise, and so we got to account for that when we are designing transmitters and receivers. You always have to account for the noise in the channel. This right here is a block diagram of a typical digital communication system. So as you can see, it's a lot more intricate than the block diagram for the analog system. And this also includes, look at this, family. So you have, your information source is formatted. You go through some encoding, some encryption, some in-channel encoding, and then look, you have multiplexing features here. Your signal gets modulated, okay? And then it gets sent through the channel. And then on the receiver end, you go through the same process, but now it's like, you got to demodulate, you got to detect, you got to decode, you have to decrypt, okay? And then you also have to do source decoding to get back the information. Okay, so it's a little bit more sophisticated than the analog system. But the essential components of a digital system will be formatting, and this is when you transform the source information into bits. Modulation is the process by which the message symbols or channel symbols are converted to waveforms. Okay, and so I know that SANETER, you had a lawyer on Friday, and she was trying to convince your audience that you can measure electromagnetic radiation using modulation. That's not true, SANETER. Modulation is simply just a process of converting, the waveforms to, you're converting the waveforms or putting them in a form that's transmittable. That's all you're doing, and so that has nothing to do with radiation in a sense. Okay, it has nothing to do with it. Demodulation is something that happens on the receiver end, detection and synchronization. All right, so what is a wireless communication system? Okay, a wireless can be defined as, it says, a descriptive of a network or terminal that uses electromagnetic waves, okay, rather than wire conductors for telecommunications. Okay, so it can be defined as transmitting or receiving information via electromagnetic waves. And I know when people hear the word electromagnetic waves, they start thinking about radiation and going crazy, but we'll get into that. So these are common examples of wireless equipment. I know we always use our cell phones. Back in the day, pagers was something that we used, but that was wireless equipment. Today we use GPS, that's wireless. You have cordless computer preferentials, home entertainment system, control box, remote garage door openings, two-way radios, baby monitors. So those are just examples of wireless equipment. This is the evolution of mobile radio communications. It started in 1897 with a guy named Marconi. He first demonstrated radio's ability to provide continuous contact with ships sailing the English Channel. And then in 1934, police adopted what they call amplitude modulations. And I know back in the day, people still listen to AM radio, but I don't listen to AM radio. But you hear people say AM radio, but what does that mean? That means that these signals are being transmitted or modulated using amplitude modulation, which means that the information is now being carried in the amplitude of the signal. So anyway, in 1934, police adopted amplitude modulation mobile communication systems for public safety in the US. In 1934, Edwin Armstrong demonstrated frequency modulation. So we hear that a lot. I'm listening to FM radio, right? And so you're talking about frequency modulation, okay? In 1940, it says that the number of US mobile users climbed from several thousand to 86,000 by 1948, 695,000 by 1959, and 1.4 million users in 1962. In 1946, you had the first mobile telephone service, which was the push to talk. I don't know if you guys remember, oh my gosh, Kyle, what was the name of that cell phone that we used to use? This was a long time.
The church.
Yeah, the chirp. And we used to chirp. And so that when you use the push to talk mechanism, that was what we call half duplex. And I'll get into what half duplex is a little later. But in 1946, you had the first public mobile telephone service, push to talk. And then in the 1950s and 1960s, you had improved mobile telephone service, full duplex. And again, I'm gonna get into that probably within the next two slides. In 1960 and 1970, Bell Labs developed the cellular concept. And that's when basically you put up base stations, and these base stations cover what we call cells. So that's the coverage area. And so Bell Labs actually developed the cellular concept back in the 60s and 70s. In 1968, AT&T proposed the concept of cellular mobile to the FCC, the Federal Communication Commission. In 1976, Bell Mobile phone service, it says poor service due to call blocking and usage over a few channels. All right. And I think this is the last slide on the evolution of mobile radio communications. But in 83, it says the first cellular telephone system, AMPS, was around, the Advanced Mobile Phone System. And so, Brother Kyle, I was wondering when I saw this, when I read it, I was thinking about the movie New Jack City. And remember when Nino Brown hopped in the car, or one of them hopped in the car, he had this huge cell phone on his head. And I believe New Jack City, it may have came out in the late 80s, early 90s, but I was thinking about that. I was wondering if they used that particular system, AMPS, at that particular time. But anyway, the first cellular telephone system, AMPS, came out. And in 84, it says the number of cellular telephone users is 25,000. In 91, it says the first US digital cellular system hardware. So then we went to digital modulation with speech. They used TDMA. In 93, they used CDMA. And I remember that when Verizon, I used to get my cell phones from Verizon, and they were saying that they were using CDMA. And so remember, guys, that code division multiple access is just a channel, access technique. And in 1994, it says the number of cellular telephone users went up to about 16 million. In 94, specialized mobile radio service was developed to compete with US cellular radio carriers. It says in 95, with the boom of CD radio and cordless appliances, and I remember this, door openings in telephones, the users of mobile and portable radio went to about 100 million people. All right, and so that's a quick overview of the evolution of mobile communications. All right, and so in those slides, you saw half duplex and full duplex. So I want to kind of talk to you about that. Okay, so you have different types of mobile radio transmission systems. You have simplex, which is communication in only one direction. Half duplex is two-way communication, same radio channel for both transmission and reception. So it's push to talk, release to listen. And so that cell phone that you were talking about, Kyle, that's a beautiful example of half duplex, right? Where you have push to talk and then you have to release to listen. But what's important is that you know that it's two-way communication, but you're using the same radio channel for both transmitting and receiving, okay? But full duplex, it says simultaneous radio transmission and reception between a subscriber and a base station, okay? So with full duplex, you have simultaneous radio transmission and reception. So you're transmitting and receiving all at once, okay? Now, it says right here, let me go back, a full duplex system, we have FDD and TDD, and let me explain what those are, okay? With FDD, which stands for frequency division duplexing, you have a base station involved, okay? So at the base station, it says separate transmit and receive antennas are used to accommodate the two separate channels. At the subscriber unit, a single antenna, and that's what we have in our cell phones, right? We have a single antenna. So an antenna is used for both transmission to and reception from the base station, okay? So it says a device called a duplexer is inside the subscriber unit to enable this. So you have one single antenna that's used for transmitting and receiving, but at the base station, you had separate transmit and receive antennas, okay? So then you have a concept called the forward channel and the reverse channel. The forward channel would be from the base station to the mobile user, and the reverse channel would be the mobile user to the base station. You also have TDD, time division duplexing. Okay, so that's a type of full duplex system. So with the TDD, a portion of time is used to transmit from the base station to the mobile, and the remaining time is used to transmit from the mobile to the base station. All right, so it's only possible with digital transmission formats and digital modulation and very sensitive to time. Okay, so you can't use analog for a TDD system. It says it's recently been used only for indoor small area wireless applications where the physical coverage distances are much smaller than much smaller than the many kilometers used in conventional cellular technology. So really for small areas, okay? And that's what they would use TDD for. Now, a good example of an FDD system would be your cell phone, okay? And so you see from this diagram that you have, a user here. The user might be here. This user is communicating with the base station. This base station is covering a particular area, but these base stations are connected to something called a mobile switching center, which is connected to the public telephone network and internet. All right. And so the MSC, which is called the mobile telephone switching network, it coordinates activities of the base station and connects to the entire cellular system. It connects the entire cellular system to the PSTN. So, and the PSTN provides the communications infrastructure to carry the voice and data locally, nationally, and internationally. And that's what we see right here. So you have the cells cover a particular area, and that base station is connected to the MSC, and the MSC is connected to the PSTN. All right, so they communicate, and let me go back to the diagram. Notice right here, it says that, they communicate via an air interface, which is a physical or link layer protocol. So some sort of protocol, some sort of standard, okay? And that standard is called the Common Air Interface, right? That is the standard that defines the communication between the base station and mobiles, and it specifies 4 channels. So SANETER, I remember when Polite was on, he was on last week, and I was talking to him about these 4 channels, and talking to him about the MSC and the PTSN. Okay, but anyway, so the CAI, the Common Air Interface, specifies 4 channels. Again, you have forward channel and reverse channel, but you have something called forward voice channels and then forward control channels. Okay, and so the forward voice channel is used for voice transmission from base station to mobiles. Okay, reverse voice transmission, these are channels used for voice transmission from mobiles to base stations. Okay, forward control channels are used by base stations to page and locate the mobile, set up calls, and it moves it to unused channels. Okay, the reverse control channel is used to respond to the page sent by the base stations. So SANETER, you asked me on the spot, you said, well, Dr. Maat, how do cell phones work? And I said, well, SANETER, I said, right now, you are connected to a base station, and that base station is connected to a base station that is then connected to my mobile cell phone. And I explained to you that's how it works, okay? So what happens when we make a telephone call? Well, cell phones have codes inside of them. You have something called an electronic serial number, an ESN, okay? Which is a unique number that's programmed into your phone when your phone is manufactured. You also have something called an MIN number, a mobile identification number, which is a 10-digit number derived from your phone's number, okay? You also have a SID, we call it a SID, a system identification code, which is a unique 15-bit number that is assigned to each carrier by the FCC, all right? And so when you make a telephone call, the first thing that happens is this: you switch on your mobile phone and it tries for SID. And I'm going to say SID, and I'm going to use these acronyms at this point because I just described what they are, okay? And so when you turn on your telephone, it's looking for SID on the control channel. And so at this point, let me go back. I've already defined for you what a control channel is, right? Okay, so we should know. So I'm just going to kind of flow at this point. So when you cut on your telephone, it tries for SID on the control channel. The control channel really is a special frequency that the phone and base station use to talk to one another. So if the mobile phone finds difficulty trying to link with the control channel, it displays no service. And that has happened, I'm pretty sure, to some of us or a lot of us when we've tried to make phone calls. You won't get service. Well, that means that your phone cannot locate, it can't get a SID on a control channel when you get that message. Okay, so if the phone gets a SID, it compares the SID with the SID programmed in the phone. If both SIDs match, then the phone identifies that the cell it is communicating with is part of the home system. If they don't match, that means that the phone is a part of another system. So then you'll get a message saying that you're roaming. Okay. So anyway, 3, it says the phone also transmit a registration request along with the SID in the MTSO. So in my previous slide, I had MSC, but this is still mobile telephone switching office. Some people just say mobile telephone switching center, and they'll shorten it and use the acronym MSC, but MTSO and MSC are all the same, okay? And so it says the phone also transmits a registration request along with the SID, and the MTSO keeps track of your phone's location in the database. So the MTSO or the MSC, it knows in which cell you are in when it wants to ring the phone, okay? So the MTSO then gets the signal, it tries to find the phone, okay, that you're trying to call. And it says that the MTSO looks in its database to find the cell in which the phone is present. So once they find the cell, it says the MTSO then picks up a frequency pair to take the call. the MTSO communicates with the mobile phone over the control channel to tell it what frequency to use. So this is what would happen, what would be happening on your end, SANETER, okay, if I were to call you. So it's trying to basically, the MTSO is trying to coordinate between the base stations. They're trying to coordinate the call between base stations. We're trying to connect the call between base stations. So it says the MTSO communicates with the mobile phone over the control channel to tell it what frequencies to use. Once the mobile phone and the tower switch on those frequencies, the call is then connected. So during this process, you're hearing the ringing in your ear, and that's what's happening, okay? Your phone, you have the MTSO, they're trying to connect the calls between base stations. All right, 6, it says when the mobile phone moves towards the edge of the cell's base station will note that the signal strength is diminishing. So if I'm talking to someone on a cell phone and I saw moving away from the base station, the signal strength or my signal strength is going to decrease, okay? And so then at that point, the base station says, hey, I gotta move this call to the nearest base station. We call that a handoff, okay? So it says at the time, the base station in the cell in which the phone call is, or the phone is moving, will be able to see the phone's signal strength increasing. So what happens is they do a handoff, and it says the two base stations coordinate themselves through the MTSO. At some point, the mobile phone gets a signal on the control channel and directs it to change those frequencies. This will switch the phone to the new cell. So the process that they are describing in this document or in this article is really a handoff, you know, when you're moving from cell to cell. And so basically, this is just a picture of what I just described. Again, SANETER, I'm over here in my dress, you're over here. And so when I make a call, and this is what I said to you live, I said, SANETER, we're really communicating between two base stations through an entity that we call the MTSO, or some people call it the MSC. And this is what I explained to you last week. But somebody said that I was wrong. I don't understand how. These are the facts, family. All right, so now let's get into electromagnetic radiation. I only have maybe like 4 or 5 slides left. So family, bear with me. Okay, so inside of your cell phone and even other devices, right, that utilizes cellular technology, you have a transmitter, okay? And the transmitter encodes the sound of your voice onto continuous sine waves. And so we've already defined what a sine is. I actually showed you a sine wave in the beginning of the presentation when I illustrated or showed you a continuous time signal. You were looking at an actual sine wave, okay? And so the transmitter, says inside of a phone, encodes the sound of your voice onto a continuous sine wave. The transmitter sends the encoded signal to the antenna, which sends the signal out using radio waves. And radio waves are made up of electromagnetic radiation, okay? Energy, electromagnetic energy, okay? And these radio waves are composed of electric fields and magnetic fields, and they have electromagnetic radiation energy, all right? So electromagnetic radiation, it says, is comprised of waves of electro and magnetic fields moving at the speed of light, okay? And so this is the equation for the speed of light. The speed of light is equal to C times lambda times F, okay? And so lambda is the length of the wavelength, and F is the frequency of the wave, okay? And I believe that C, the speed of light, is equal to 3.0 times 10 to the 8. Kyle, correct me if I'm wrong. I never remember numbers. I believe that the speed of light is 3 times 10 to the 8. I think that's what it is. It says electromagnetic radiation can be described using 3 quantities: energy, frequency, and wavelength. Brother SANETER, you had the lawyer on your show last week, and I asked her, how do we, measure, how is electromagnetic radiation measured? And so when she started talking about it, she was describing it in terms or in the context of human beings. I was asking her about the wave itself. And so I don't know if my question wasn't clear. I don't know if she didn't hear me, but I wasn't talking about with respect to human beings when I asked her, how do you measure radiation, electromagnetic radiation? I was simply asking, like, how do you describe it, right? Or how do you measure it? How do you measure the electromagnetic radiation of a wave? And so it can be described using 3 quantities: energy, frequency, and wavelength, okay? And so you hear the brothers on the platform talk a lot about electromagnetic radiation. We know there are two types, ionizing radiation and non-ionizing radiation. So ionizing radiation is a type of energy released by atoms that travels in the form of electromagnetic waves or particles, okay? So it says ionizing radiation can remove electrons from the atoms, i.e. they ionize the atoms, causing the atom to become charged and ionized, okay? Non-ionizing radiation, it says radiation in the part of electromagnetic spectrum where there is insufficient energy to cause ionization. So remember, ionization is when you're removing electrons from the atoms, okay? Okay, causing the atom to be charged to ionize. With non-ionizing radiation, that doesn't happen. So it says that non-ionizing radiation includes electromagnetic fields, radio waves, microwaves, and optical radiation, which consists of infrared, visible, and ultraviolet radiation. Okay, so this is just a chart that shows the different the two types of radiations, the definitions, the forms, and some source examples. With non-ionizing, you're dealing with low to mid frequency radiation. Is typically or generally perceived as harmless due to its lack of potency. And this is where like cell phones, a lot of these wireless devices fall. They fall under this category of non-ionizing radiation. Ionizing radiation is mid to high frequency radiation. It says which under certain circumstances can lead to cellular and DNA damage with prolonged exposure, okay? And so typically you're looking at, your UV rays, it says X-rays, gamma, okay? It's up here with non-ionizing. We have RF signals, microwaves, visual light. And so source examples of non-ionizing would be your microphone. We always use microphone. Your computers, your house energy smart meters, your Wi-Fi network, cell phones, Bluetooth devices, power lines, all right, MRIs. And so all of this will fall under non-ionizing radiation. And again, they perceive non-ionizing radiation as harmless, okay? Ionizing will be sunlight, X-rays, and it says some gamma rays. So let's look at the electromagnetic spectrum of the devices that we commonly use. We use cell phones every day, televisions, microwaves, infrared devices when you have your remote control. So this is the stuff we use every day. And these devices are operating at a low frequency, okay? So it's emitting what we call non-ionizing radiation. But here, these devices are moving at a very high frequency, okay? And this is where the ionizing radiation would fall on the spectrum, okay? And those would be, that's ultraviolet radiation. If you take X-rays, radioactive waste. So let's look at where 5G falls under. And I know that Brother Jabari, he took this, he showed this diagram last week when he was having a conversation with Defna, I think her name was Defna, and Brother Curtis Koss. He showed this diagram that he took from the New York Times, but the New York Times took the diagram from the National Aeronautics and Space Administration, National Academies of Sciences, National Institute of Environmental Health Sciences, okay? So they took it from there. All right, but let's look at where 5G falls in the spectrum. And this is what you were talking about, Brother Kyle, in your presentation. It falls between 3 kilohertz and 300 gigahertz. So we're still here at the bottom of the electromagnetic spectrum, okay? The non-ionizing spectrum. So here lies the concern with people. And I totally understand, SANETER, why people are concerned, because human beings absorb an amount of radiation. So we have these devices that are emitting radiation, non-ionizing, ionizing, it doesn't matter. These devices are emitting radiation. So it's emitting this energy and we are absorbing this energy, okay? Now it says here that exposure to high levels of radiation can adversely affect human beings. But the key word here is exposure to high levels of radiation can adversely affect human beings. Okay, now it's something called the specific absorption rate. We call it the SAR or the SAR. That's a measure of the rate of RF energy absorption by the body from the source being measured. So typically, they do have this quantity that they measure called the SAR or SAR. Okay, and the SAR is typically measured in watts per kilograms. Okay, but what I want to bring to your attention is this, family: a device with a low SAR value does not imply that it's safer than a device with a high SAR. Okay, SAR values are just used; they're simply used by the FCC to ensure that the cell phone doesn't exceed FCC maximum permissible exposure levels. So they know that you're being exposed to this radiation. They know that your body is absorbing a certain level of radiation. What they do is they use these SARs, or the SAR values, to ensure that that cell phones and other devices don't exceed their maximum permissible exposure levels. And so I totally understand the concern right here. But anyway, I think I have one more slide, and this is actually how the SAR is measured. It's measured in watts per kilogram. So SAR is equal to sigma times E. So sigma is the electric conductivity, okay, in Siemens per meter over rho, and that's equal to C, and C is the specific heat in joules per kilogram per Kelvin. So C is multiplied by, we call this a derivative in calculus, family. So you're taking the derivative of temperature with respect to time. So you can either compute it using the electric conductivity, and rho, which is the mass density, and E, right, which is the energy, or you can calculate the derivative, which is C times the derivative of T with respect to dt. So it's two ways that you can calculate that. So anyway, Brother SANETER, I totally understand what the concern is. People want to know, well, look, we are absorbing this radiation. Will it impact us in the future? What I can say is this, family. Right now, scientists are saying that we shouldn't be concerned about it. But what may not be a concern today may be a concern tomorrow. So I'm not going to definitively tell people that all of this stuff is harmless. I wouldn't take that position. But the position that I will take is that right now, scientists are saying that the radiation levels aren't harmful. And so what I want to do right now, family, is bring in Brother Kyle to talk about the International Commission on Non-Ionizing Radiation Protection report. So Brother Kyle, I'm gonna hand it over to you, King.
All right, thank you very much. And that was a beautiful presentation. I hope everybody that was in the chat that was listening got something from it. If you didn't, that's why we had to call in.
All right, Kyle.
Yes, sir.
You have to come on in. Unshare your screen, doctor.
That's what I'm trying to do right now, so I don't understand.
Go at the top where it says stop sharing.
I know my screen froze on me. I know how to do it. I'm telling you, my screen froze on me for some reason.
So go out and come back in or something. See if that works.
All right, so give me a sec.
One, two, y'all there?
Yeah, I'm here.
Okay, come on in, brother.
Let me see. Can you see me?
No.
My camera should be on. I'm not sure how to come in because I'm already in the Zoom.
No, I think Dr. Maat, like she said, her screen is on. There you go. You're in the building.
All right, peace, family, peace. I want to go ahead and share my screen as well to address some of the issues because I was kind of reading in the chat and I did see some issues or questions that are relevant issues in my personal opinion. All right. Kind of want to just bring up, the people. So a lot of people are asking, is it safe at certain levels? And what about the millimeter wave band? So with the millimeter wave band, what that is, it's a particular frequency that ranges from 30 gigahertz up to 300 gigahertz. And what we have is we have an international body. It's called the ICNIRP, International Non-Ionizing Radiation Council for Protection, and what their job is they actually have done several reports, but the most recent report was a 10-year study that they did to pretty much analyze and determine what frequencies would be harmful and what would be non-harmful in that spectrum. So the first slide that I want to share just regarding the frequencies, if y'all can see, and it shows us here in the United States of America. What we use here is a median of 2.5 gigahertz. That's currently in 2020. So like I was saying earlier, it starts at 30 gigahertz all the way to 300. Right now, we're only using 2.5 as an average. So we're nowhere near that area that could be potentially dangerous to anybody based on the standards that was given from ICNIRP. Also on this, it actually shows a snapshot of what is currently being licensed and what's unlicensed. As you can see here in the blue, these are current licensed spectrums versus the ones that we use and the ones that are unlicensed. As you can see, we don't have anything that's licensed above, I believe it's 48.2 gigahertz. So that's very important because a lot of people are actually looking at reports and they're making these assessments based on things that are at 300, 200, 100 gigahertz, but we're at 2.5 currently. Now, the reason why we will bump up to a higher frequency because we would need more bandwidth. The more devices that you get onto a network, the more it's going to slow it down. Same thing applies when you're looking at your home internet or your Wi-Fi. Your Wi-Fi at home may run from 2.4. Even if you have a dual band router, you see it's 2.4 and also 5 gigahertz. The reason why a person would change to a 5 gigahertz, which is a higher bandwidth, it means that there's multiple devices.
Okay, so I'll play the rest of this later on sometime tonight. Polite and Jabari's live right now. Let me see the chat. Yeah, Kansu, I think that's begging the question. So SANETER's going live right now. Yeah, I don't think there's anything wrong with questioning information. I think that's what separates us from the church or religious folks. A lot of times when I be talking about vaccines, of course, I know what I'm saying is true, and it's not comfortable when people ask, like, challenge you, because especially when you know what you're saying is true. It's never like a good feeling when somebody challenges you, but that's part of that's part of the game. That's part of the territory, is that to be challenged. So I got to like pace myself and calm down and say, okay, listen, relax. I'm not religious. My information can be challenged. Let me just, show and prove. So matter of fact, I'm going to show you my own friend. I got some close friends challenging me on viruses, and he was trying to scare me, because he works with scientists. He's in the pharmaceutical industry as well. He's like a supervisor, and he got some scientists that he works close to. So he was trying to like do some more appeal to authority. I said, bro, listen, man. I said, if your scientists are actually scientists, all they're going to do is agree with what I read, right? That's it. So you ain't going to pull some authority or pull rank. All they're going to do is agree with what I've read. So I'm going to show you the screenshots. I'm going to take his name out to save the embarrassment for him. But I'm definitely going to screenshot the conversation and show you how he shifted the goalposts. My whole thing was, how do you kill a virus if it's not alive? And he ran with that. Then watch how he shifted. Big. So this is how you conversate. So I don't mind. Well, I do mind. I don't like, nobody likes being challenged, but that's part of information. That's part of education, is to be challenged. And you got to be ready to defend what you say, your information. I'm confident when it comes to vaccination and viruses. So, for me, I don't think it'd be a problem to show and prove. But anyway, so head to SANETER. If you into that, if you're into like the debating thing with Jabari and Polite, you can go there. I'm going to miss mostly all of it because I'm going to be teaching online. Yes, Gaddafi, I'm sending you guys there if you want to go. I'll be back after that goes off. I will probably catch the end of it. So, I'll probably plan the whole thing on my live. But I hope you guys can join. Hope Kofi could join us. Hope Kasu could join us. And let's argue. Elijah Muhammad said, let's argue in the best manners. And Dr. John Henry Clark also said, paraphrasing, argue in the best manners. So you dig? And you see, I pretty much lead by example. I try my best to argue in the best manners, even when I call and challenge people, like I did Polite and Eric Muhammad. you seen, I led by example. I challenged them in the best manners. I didn't get all crazy. I was calm, and I moved on to my second question. So peace, everybody, man. Thanks for showing up. Peace, peace, peace.